Hey everyone, this video is talking a little bit more about surface area and a nice kind of general formula that you can use for this one. So I'm assuming you've already watched the intro video on kind of developing the idea or the formula for surface area, and that went through one example. I want to do something a little more generic on this one. So with surface area, remember, we have a curve and we're rotating around an axis. So let's say something like that is our curve. We're going to rotate maybe around this y-axis right here. Now there's a couple ways that you can think about it in terms of what you're going to do. So no matter what, you're going to break this up into small pieces right here. So we'll take these little pieces and we're going to rotate those around our axis. And rather than like with volumes being filled in, these are just going to be, nice, almost like shells, just that thin piece that's getting rotated around. And we want to find the surface area of that piece. So if I blow this up a little bit, this is where the idea is. I have kind of this slanted cone piece, often called a cone frustum, and that little piece we can kind of fudge a little bit. So depending on the book that you get, they may give several different arguments for what the surface area of this is going to be like. But the one I like to think about is if you just kind of average down this diagonal right here. So if we average down this diagonal, really, and just kind of straighten it out. So think of this part kind of bending in, this part bending out. Same thing here, the top bends in, the bottom bends out until those sides are straight. Then what you're going to get is basically just a nice cylinder that you get right here. And these are pretty small pieces, but for the most part it's more about just being able to average this top coming in, this bottom coming out right here. All right, so we know how to deal with these cylinders. We've done it with shells, right? So if we had, say, an axis of rotation coming down here, we know that we go out a distance r. And for this one, it'd be kind of right there in the middle, that center point. So let's go ahead and call that R. Same thing here, this distance out to that edge, that's going to be R. So with shells, remember, it's 2 pi r times the distance times the thickness. Well, with surface area, there's no thickness. So this surface area of this little piece is going to be 2 pi times r. So that gives us the circumference around. So if I were to cut it, roll it out into a rectangle, that's the length, that 2 pi r. And then the height, remember, is coming from this little slanted piece right here. And remember, this we could think of as just a little piece of arc length. So a little piece of arc length right there would be ds. So this length here would be ds down that little diagonal. If we straighten it out, we're not going to change the length of this. We're just going to kind of average it. So this part is closer, this part's further out, but the length of this is going to stay the same. So this is still ds right there. So surface area is going to be 2 pi r times ds. All right. Now, the idea is we're going to add all these up. So really, when we think of surface area, we could say this is going to be the integral from a to b. If I have my starting a, my ending point b, somewhere up here, of this 2 pi r times ds. And this is a pretty powerful formula to think about. Some books don't include all the scenarios that you might run into. So with some books, they say, with something like this curve that I want to rotate around the y-axis, get this in terms of, say, x equals something in terms of y. and then just use this distance right here as, you know, as that function value going up. But really that's not totally necessary, and it may not even be possible to solve this equation in terms of y, or certainly not very easily. So some other things that you can think about is just picking your ds. So I'm going to remind you what those little ds arc lengths were from before. So remember ds, we said it could be the square root of our dx squared plus dy squared. If I just make a little triangle there and use Pythagorean theorem, and then we simplify, well, it's not really simplified, but we made it into a more useful form with either pulling out the dx or the dy. So you get either one of these. So 1 plus your derivative dy over dx squared. Sometimes if you want to put the f prime in there, you can. I'm going to put, let's do this one first, dy over dx, quantity squared, and then the dx on the outside. So if you want things in terms of x, you would use this one. If you want things in terms of y, then I could use this dx over dy, derivative x with respect to y squared. This one's going to be more useful if you have x equals equations, and then plus 1, and then the dy. So those are the two forms I can use, and depending on which one I want to use, I can use either one of those for this ds in here. The r, remember, you can also think of in a couple of different ways. So for this one, our r would be across here, and this could be either x, or it could be your f of y. So if x is, say, like sine of y, or y cubed or something like that, then this would be what that function value is. And I can use either one. I can just say this distance is x coming over from the x-axis or from the y-axis over to this point, or I can do the actual function name if I want it in terms of y. Same thing if I were rotating around, say, this axis coming up, this would be a distance y, or the function f of x, whatever that might be. So this is kind of the idea that I want to bring up just thinking about some of these. So I'm going to do an example or two and see what we get. So let's make this more specific. Let's say we had some function, let's just say sine of x. All right, so this is y equals sine of x. And let's say we're going to rotate around the y-axis and we want that surface area. So remember, this is just this curve. There's no area underneath. There's no anything else. Just sine x from 0 to pi. All right. So what we get is going around this curve for this mirror image on this side. And this would be going all the way around, something like that. So you get this weird, like, mound shape getting rotated. The idea for us, remember, is we're not taking rectangles, we're just taking little segments here. So these little segments that we have on our curve are going to get rotated around. Need to find the surface area of those. So if I take this little segment right here, what is this distance right here? That's my r. And then what is the ds that I get for that length? So I need both of those, the r and the ds. Well, this is y equals sine of x, so it's going to be easier to use this one right here, where I have ds is that square root of 1 plus dy over dx squared times the dx. So let's go ahead and try that. We'll get this integral from 0 to pi of this 2 pi r ds, and I'm going to replace that ds with this guy right here. So let's say integral 0 to pi of 2 pi. I'll leave a space for the r, or actually let's just write it in, and we'll write in the generic over here. So square root 1 plus that dy over dx squared, and then dx on the outside. Alright, so the dy over dx, that's not too hard to do. Right, derivative sign is cosine, so this will be cosine x. So I'll go ahead and replace that in there. So we got this integral 0 to pi of 2 pi. We'll leave space for our r right there, and then go and put this in 1 plus, and a cosine of x quantity squared, that's going to be, let's shorten it, cosine squared x, and then the dx. Now remember, I want everything in terms of x. So when I'm looking at my r, how far over from the y-axis is this segment? Well, it's a distance of x. So that's all I have to do. I don't have to try to change this into x equals in terms of y, which would be a little problematic anyway, because inverse sine has a domain from negative pi over 2 to pi over 2, so you gotta do something weird on this right hand side. So that would be problematic in itself, trying to rearrange. But if I just take that r as what it is, that distance x, then I can just replace it right there. All right, let's do one more with a different axis of rotation. All right, so let's say I'm trying to rotate this curve y equals sine x, we'll use that again, but around the line y equals 3. So again, I'm just going to take some of these short segments, maybe I'll draw one in, this arc length right here, and I'm going to need the r going up to here, and the length of that segment ds. So we're still using the same 2 pi r ds, but now the ds, what do we want to put in? Well, I really don't want to rearrange this again, so I'm going to use that same one. ds is that square root 1 plus dy dx. That's the easy derivative to take, and just use that. So this is going to be integral, go 0 to pi again. So that's where we're going, 0 to pi. And we'll say 2 pi. I'll leave space for my r again, so we'll just put in the r. And let's just write it out. This 1 plus dy over dx quantity squared, and then the dx. All right, so that dy over dx I can replace with same thing. Derivative is cosine x, so I'll just put that in. So we got integral 0 to pi, 2 pi. Again, I'm going to leave space for the r, and we'll get that 1 plus cosine being squared, so cosine squared x dx. All right. Now what do I want to put in for my r? Well, remember, coming up from the y-axis, or sorry, the x-axis, that distance is y. And going all the way up here, that distance is 3. So when I subtract that 3 and that y, what I'm left with is this r is just 3 minus y. So that's what I'm looking at right there, is this r distance that I'm going up is the same as this 3 minus y. So those two are identical. So right there in that parenthesis, I'll put 3 minus, but I don't want y, right? I want stuff in terms of x. So rather than putting in a y, I'll go ahead and just write it. I'm going to replace that y with my definition, which is sine x. So our final would be integral 0 to pi of 2 pi times this 3 minus sine x, because I have a dx, want everything in terms of x. And then that square root of 1 plus cosine squared x dx. All right. And again, to evaluate, you just use Desmos or your calculator, plug that in. We're not doing these guys by hand. But that is the setup. So hopefully that makes sense, gives you a little more tools to use than what you might see in the textbook.